Hello.
Hello, good afternoon, ma'am.
Good afternoon.
आपने साइन किया है?
चेक करेगा Hello.
Hello.
Yes. Yes. Here is afternoon now.
Afternoon now.
Hello.
Hello, I'm here.
Hello. Hello, madam. Am I audible?
Hello.
Hello,
Yes,
madam. Am I
I can
audible?
hear you. Yes, I can hear you.
Okay. Yes. You are also very. Your voice is also clear. And good afternoon to you.
Good afternoon.
Hello.
Hello.
And good morning. Because in your
Yes,
place is the
here
morning.
Good morning. Good morning.
Nice to see you,
Nice
madam,
to see
again.
you too. Thank you for the
Yeah.
invitation.
Little bit it is now delay. Okay.
Okay.
But now we are starting. Okay, na?
Okay, no problem.
Yes. Thank you.
Thank you.
Yes. Good morning. Because in your place is the morning.
और एक केमिस्ट्री का काम है To commence the proceedings, I respectfully invite our esteemed chairperson, Dr. Prashant Thakre, and co-chairperson, Dr. Satish Chandra Ravid, sir, to kindly take their seats on the dais.
Prashant Thakre.
It is my privilege to introduce our first chairperson for this session, Dr. Prashant Thakre. He is highly experienced physician serving as the chairperson, Dr. Prashant Thakre, and co-chairperson, Dr. Satish Chandra Ravid, sir, to kindly take their seats on the dais. He is serving as an assistant professor at the Mumbai University. He is our first chairperson for this session, Dr. Prashant Thakre. He is highly experienced physician serving.
Yeah, ma'am Sonia, is it audible to you?
Yes.
Oh, thank you very much. That's great. So most welcome here because here we are in Santaji Mahavidyalaya Nagpur, and it's afternoon. I came to know that this morning they are in
Yes.
your place in Portugal.
Yes,
So
it is.
is it audible to you?
Yes, I'm hearing you.
Okay,
Yes.
thank you very much. That's great. So most welcome here because here we are in Santaji Mahavidyalaya, Nagpur. And it's the afternoon. I came to know that morning there in your place in Portugal.
Yes, it is morning here.
Yeah, it's our great pleasure that we are having you as a keynote speaker for this invited talk, that is session 3. Ma'am Sonia graduated in applied chemistry from the Nova School of Science and Technology, that is Portugal, and she got her PhD in chemical engineering in 2001 from the same institution. She carried out postdoctoral research at Leiden University, Netherlands, and at the University of Lisbon, Portugal. She was in 2019. She was an invited from University, China, since 20. Is it audible to you, ma'am?
Yes, now it is again. Yes, now it
Yeah,
is.
yeah, fine. Please proceed. Please.
Okay, can I start then?
Yes, sure.
Okay,
You
thank you.
start.
Okay, I'm going to share the screen. Okay. Thank you very much. Yes, now it is. Yes, now it is.
Yeah, fine. Please proceed. Please.
Okay. Can I start then? Thank you very much
Yeah,
for this
sure.
nice introduction. Okay, so I'm going to talk about highly efficient graphene oxide, zinc oxide, lignite catalyst for photocatalytic degradation of methylene blue and gentian violet that are two cationic dyes. So this is a collaboration work done between my University of Portugal and some universities of India in Durg and Raipur. So as this was also a conference in India, I thought it was interesting to show this collaborative work between Portugal and India. So we use this interesting composite, graphene oxide, zinc oxide, and lignite catalyst to photocatalytic degrade these two dyes, cationic dyes, methylene blue and gentian violet. Concerning the global sustainability contest, it is important to understand that there are currently some water pollution challenges all over the place, and that there is a large need for green remediation. Therefore, the photocatalytic degradation is a fast, efficient, and cost-effective way to remove dyes from wastewater. Okay, so it is very important in wastewater treatment. So that's what we use in this. And the performance of nanoparticles, okay, is influenced by their shape, by their size, and by surface area to volume ratio. And the incorporation of nanoparticles into polymer matrices allows to achieve enhanced functionality, enhanced stability, and enhanced traceability. Nanocomposites that are made of several different materials can have high surface area, very good tunability, and also multifunctionality. They can be used for a variety of applications. And some examples are here, can be in catalysis, we use, can be in the electronics, in photonics, biotechnology, nanomedicine, and also, as we use in this work, in wastewater treatment. Zinc oxide was one of the components of the composite catalyst that we use. And it is a very important material because it has a low production cost. It's rapid catalytic activation, is widely studied, and it has applications in water-based systems that are aimed at degradation of organic pollen. It also has a wide band gap, okay, which lies in the ultraviolet range. But nanoparticles, when it's in the form of nanoparticles, they usually show a reduction in the band gap, okay? So zinc oxide has a band gap of from 3.2 to 3.4 electron volts, but nanoparticles usually have lower, in 2.5 to 3 electron volts, compared to the Boss zinc oxide, because it's due to particle size, doping, or surface modification. So this reduction in the band gap allows the zinc oxide nanoparticles to observe invisible light, in addition to ultraviolet radiation. And therefore, the catalytic performance of zinc oxide under visible light radiation can be further enhanced through the incorporation of other additives or dopants, which has proven already to be an effective strategy to tailor and improve photocatalytic activity. So, in this work, what we did was exactly that. What we did was to use the incorporation of other materials as well. And so, one of them was the graphene oxide, because it's environmentally friendly and widely accessible. It's also very versatile because it has large surface area, has excellent mechanical strength, has abundant oxygen-containing functional groups, and these groups, they provide active sites for chemical reactions, for absorption, and for interaction with other materials. And it is also a semiconductor with tunable electronic properties depending on the degree of oxidation, of course, and it can facilitate electron transfer in photocatalytic and electrochemical processes. Also, its optical range can be extended into the visible range, and also its photocatalytic performance can be enhanced through reduction, functionalization, or combination with other semiconductors like zinc oxide. And graphene oxide is also widely studied for applications in water treatment, sensors, energy storage, and in composite materials. So, apart from the zinc oxide and the graphene oxide, we also use lignin, which is a renewable and very abundant biopolymer that is derived from plant biomass. Okay, it is very present in plants. And it has a complex aromatic structure that is rich in phenolic and methoxy groups, and this makes it a good antioxidant, UV absorber, and potential photocatalytic enhancer. Also, lignin can interact with nanoparticles or semiconductors and improve dispersion and stability in composites. Therefore, the incorporation in photocatalytic or absorption systems can help in the removal of organic pollutants, also enhance light absorption and provide more active sites due to those functional groups. The composites that you use, zinc oxide, graphene oxide, and lignin, has a synergistic effect. Why? Because we use the zinc oxide, okay? It is the cell we call the engine, okay? It is the core semiconductor providing strong intrinsic photocatalytic redox capability. Okay? And then we use graphene oxide, which is a conductor. So it provides a large surface area, excellent electron transport, and pi stacking capacity. And we have also lignin, that is the biobinder, okay, and it's a sensitizer. So it is a sustainable biopolymer that offers abundant functional groups for pollutant scattering and also natural visible light sensitization and structural anchoring. So here we have like an artistic conception of the of the graphene oxide sheet with the zinc oxide flowers, shall we say, flower-like. Okay, here we are going to see some images, they look like flowers. And the lignin, that is those polymers that is, keeps it there. So an artistic composition, an artistic design, shall we say. Okay, the synthesis, it was performed in one-step hydrothermal integration. So the first part, the precursors, okay, from graphite, okay, we use the modified Hammer's method, okay, and then to obtain the graphene oxide. From the zinc nitrate, okay, by chemical precipitation, we obtain the zinc oxide nanopart. And the phase 2, it is the dispersion. So we put the graphene oxide ultrasonically dispersed in water, and there was a dropwise addition of zinc oxide and the continuous stirring. Then in phase 3, we integrated the lignin, okay? We added the biopolymer, it was ultrasonicated for 30 minutes, and then with 48 hours of continuous stirring to obtain an homogeneous dispersion. Finally, there was the hydrothermal treatment, centrifugation and ethanol wash, freeze-dried, and then we obtained the ternary composite. Okay, so this synthesis protocol ensures a true exfoliation, strong electrostatic interactions, and a high uniform distribution of active sites across the composite matrix. The characterization involves chemical characterization, structural and morphological characterization. So, starting by XRD, X-ray diffraction, we have here the result for the graphene oxide, the graphene oxide with zinc oxide, and finally the ternary composite, graphene oxide, zinc oxide, and lignin. And what we see is that pure graphene oxide, okay, at the bottom, it has a characteristic peak and at 10 degrees, to theta equal to 10 degrees, and it's the 001 reflection, okay? So it shows a well-ordered layer structure as expected. But then the graphene oxide, zinc oxide has that peak the graphene oxide peak. You can see it there at the beginning of the spectrum, but also as expected, multiple zinc oxide reflections that correspond to the planes of the hexagonal zinc oxide, which is vertical. And the most intense one is at 36 degrees, more or less, and it's the 101 plane. So it confirms the successful synthesis of zinc oxide within the graphene oxide. Finally, the ternary composite on top, the top spectrum, it shows similar peak positions to the peaks of zinc oxide, which shows that there was successful incorporation with the lignin, but the crystalline structure was not disrupted. So using the Scherer equation applied to the most intense peak, which is the 101, we calculated the crystalline sizes, and they were around 20 nanometers for the dual oxide and 18 nanometers for the composite. So this light size reduction suggests that lignin acts as a ground inhibitor during the zinc oxide crystallization. That's what we obtained. As for the sphere spectrum, we have here also the results, and we see that at higher wavelength, we have the band of the OH stretching. At middle, we have the double C bond stretching, vibration, and also the CH bending. And at higher, at the lower wavelength, we have the CO stretching and also CO and GNO vibration. So that is expected. So the few results confirm the successful synthesis of the ternary composite and the effective integration of its components. So again, I'm showing the artistic conception of the ternary composite. And here you see some images of the composite, some STEM images. So you see there that here on the right, you see that there is like this flower-like structure, you see. So that's why we made that artistic drawing of the flower. And we see also the ADX results. We have mostly carbon, oxygen, and also zinc. So these flower-like zinc oxide nanostructures that are observed, they show that zinc oxide was grown on the wrinkled graphene oxide sheet, and they are dispersed across the substrate, and lignin serves as a binder and also enhances the surface roughness. We use two dyes, two cationic dyes, okay, and one of them was this one, methylene blue dye. It's one of the most widely used cationic dyes in photocatalytic studies. It's highly stable under visible light, and it's a persistent organic contaminant in wastewater. And another dye that we used was Gentianium violet, that is also called crystal violet. Okay, it's also a cationic dye, very stable, and also a persistent organic contaminant in wastewater. So we use both to test. And we performed a photocatalytic study of the cationic model dyes degraded by sunlight irradiation. So the effect of the pH, okay, here we can see in the left in the methylene blue and in the right in the gentian violet dye. And we can see that at pH 10, okay, that was the best result, okay, for an initial concentration of 15 ppm, 0.03 catalyst amount, and for 30 degrees temperature. So the improvement under these alkaline conditions can be attributed to the increased generation of hydroxyl radicals, so OH radicals, that are the primary oxidation species in this photocatalytic process. And the similar pH trends observed in both dyes, because you see that the percentage of degradation grows with pH growth independently of the dye. So this similar trend observed for both dyes suggests that the nanocomposite surface properties, rather than the molecular structure of the dyes, it's the primary factor that is governing the photocatalytic behavior. So this was the effect of pH. We also tested the effect of the catalyst dose. So we see here both for methylene blue and gentian violet, and the results are again similar. Okay. We see that increasing the catalyst dose enhanced the degradation efficiency, yes, but the highest dose was observed for 0.3, 0.4 per 20 milliliters. And this, like that, we achieved around 95% degradation, again at 15 ppm and 30 degrees. So this improvement is attributed to the increased number of active sites and the expanded photocatalytic surface area at this higher doses. As you see, 3 or 4 is more or less the same, so it's already stable, so no need to increase more. Okay, so 3 is enough, 3 for it. We also have here the effect of the dye concentration. Okay, if we have different concentrations experiments done with different concentrations of dye. So we see that at higher concentration, okay, more dyes compete for a fixed number. So you see, as we increase the dye concentration, okay, it is more complicated to degrade, of course, because there are more molecules present, okay, and they are competed for the same amount of active sites in the catalyst surface. So that reduces the likelihood of the individual molecules to interact with the catalyst. Okay, there is more competition. And also increased dye concentration also leads to a larger light absorption by the dye molecules themselves. And this limits the availability of the photons for catalytic activity. So we use 0.03 grams of catalyst. As we saw, 0.03 and 0.04 were similar, so we use less, of course, not to waste. And again, we use the 30 degrees, and we saw that the degradation time was 60 minutes. As for here, the degradation kinetics, okay, we obtained here for both dyes a Langmuir-Ilscher first order kinetic model analysis. So the equation used was this one, okay, and the high R2 values, the coefficient, correlation coefficient of both of them, so 0.99 point something, confirm that the reaction rate is primarily governed by the absorption of the dye molecules into the saturated catalyst surface. However, we saw that methylene blue has faster degradation, okay, than gentian violet answers the same parameters, which are these ones, so that we already saw. Comparing reusability, okay, cycles, okay, we see that, of course, there is some degree of decreasing, some degree of deactivation. The activity decreases, okay, with the cycles. But we see here that we compare graphene oxide, the yellow, zinc oxide alone, the purple, the dual composite, graphene oxide and zinc oxide, the green, and finally the ternary composite with lignin that achieved the best results. And it has very good recyclability, and it retains approximately 80% of its initial photocatalytic degradation efficiency in the fourth cycle. So this is quite good. These are the results for the methylene blue dye, okay? And they are similar to those obtained for the gentian violet dye degradation. So for simplicity, I'm showing only one. As for the photocatalytic method, okay. First, okay, we saw that there is the pi-pi stacking interaction, okay? So the aromatic rings of the graphene oxide, they enable strong pi-pi interaction with the aromatic structures of the pollutant molecules, okay? And the zinc oxide provides positively charged sites that attract the negatively charged pollutants, facilitating adsorption. And hydroxyl and other polar groups present in lignin, okay, they form hydrogen bonds with functional groups in the pollutant molecules. Okay. And there is a synergistic effect. The combination of the graphene with the zinc oxide, with the lignin, okay, enables multiple simultaneous interactions. This is pi-pi stacking, electrostacking interaction, and the hydrogen bond. So it results in an enhanced pollutant adsorption and degradation, which is quite good. So the composite plus the lignin, we have the first graphene oxide pi, the pollutant DNO linking, and then pollutant lignin complex is done. Concerning the photocatalytic system, okay, we have the OH radicals, hydroxyl radicals. They are the primary oxide. Yes, they can be scavenged by isopropanol, and only them, they result in around 75 to 85 inhibition of degradation. Then we have the O2- radicals. Okay, they are secondary oxidants. They can be scavenged by benzoquinone, and they are responsible for 45 to 55% inhibition. We have also the whole H+. They can be scavenged by EDTA, so ethylene 3 ethyl acid, okay? And they are responsible for 25 to 35% inhibition. And we also have the electrons that can be scavenged by K2Cr2O7, and they are responsible for 15 to 25% inhibition. Therefore, the antioxidant properties of lignin, they stabilize these reactive oxygen species, and they are responsible to maintain a high sustained concentration of the hydroxyl radicals, okay, that are used for the total dye annihilation. Here, if we compare the results, we have here the results for the pure lignin, okay? We see that it has a removal efficiency of 35 to 45. The separation time is 60 minutes. We find it more difficult to separate. It can be reusable up to 1 to 2 cycles only, and it's stable from 4 to 8 pH values. Okay, if we have pure zinc, the removal efficiency is a bit higher, 45 to 55. Separation time takes 15 to 20 minutes. Can be reused up to 3 or 4 cycles. And stability is pH from 5 to 9. If we have graphene oxide alone, it can remove 65 to 75. Okay. Separation time, very long, more than 1 hour. Can be used for 2 to 3 cycles. And pH 3 to 10. If we have the binary graphene oxide, zinc oxide, the removal efficiency increases. Okay, it's from 80 to 85. Very good. Separation time 10 to 15. Okay, 4 to 5 cycles, and pH from 4 to 11. Finally, if we have our ternary composite, graphene oxide, zinc oxide, lignin, the removal efficiency is from 90 to 95. Very much. a very large increase. Separation time is 5 to 10 minutes. Why? Because it uses a magnetic separation. It can be separated like that, due to the properties of the zinc oxide in that calcite. Can be reused up to 6 to 8 cycles. We tested it, okay? And the pH stability is larger, from 3 to 12. So we see here that adding linen, okay, the linen shield, shall we say, acts as a critical stabilizing agent, okay, because it forms stable carbon-oxygen zinc coordinate bonds. So it is able to preserve the structural integrity, also prevents the nanoparticle integration, and ensures long-term photocatalytic resilience, because it's a polymer, so it has that power, shall we say. So very interesting results to compare between all the materials and see the synergetic effect of the ternary composite. It's quite amazing. Also, if we do a comparison with literature, okay, you see, okay, we start from the left, we see the longer reaction time, the longer treatment time, okay? If we go to the right, it's lower time, okay? So we see that linen with graphene oxide from literature has almost 3 hours, okay, around 180 minutes, okay? So it's around 3 hours. It takes 3 hours to remove, and it removes 78, around 79%, okay, of the dye. And if we compare iron oxide with reduced graphene oxide, okay, we have around 1 hour and a half, 88%, not so bad. Then if we have the iron oxide in biochar, we have 75%, 150 minutes. If we have the graphene oxide cellulose, we have 2 hours, okay, 70%. The best ones are the mixed oxides of manganese and iron in graphene oxide. They achieved a separation time of around 60 minutes, okay? They are quite good. However, our ternary composite achieved larger separation of around 98% in 60 minutes. In fact, it was not really 60 minutes, it was a bit less, around 50, but okay, let's say it was similar to the other one, but higher. So it has operational superiority compared with solid. This has a sustainable impact because we are trying to get clean water. This can be called green material because linen is green, the zinc oxide is highly abundant, and so on. Graphene oxide is also more or less. So we can see that, and we use the renewable energy. So the conclusions are that our composite has excellent efficiency, okay? It can reach 97% degradation of cationic dyes under irradiation in around 1 hour, okay? It has a good synergy because it simultaneously uses zinc oxide, graphene oxide, and linen that has those synergetic effects that leads to higher activity. It also has a radical dominion because the molecular attack and destruction of pollutants are almost exclusively done by the massive generation of the hydroxyl radicals. That's why we need that's why high pH is better. And it can be used, possibly used in an industrial process because it can be recycled. It maintains 80% of its oxidative power after 4 cycles. So it allows easy separation and a continuous. And I thank you for your attention, and I invite you to visit Portugal, which is a very nice place. Okay, thank you. I'm sorry, I cannot, I see you, Dr. Prashant. I see you, but I cannot hear you.
Repeat. Uh,
I, I see that you are talking, but I cannot hear you. I'm sorry.
no, it's okay.
I cannot, I see you are talking, but I cannot hear you. I don't know. It's silent. I'm sorry.
Great. Uh, yeah, and, chemical
Well, I cannot hear you, but thank you for the invitation. It was very nice to be here. Thank you. I wish you a successful follow-up of the conference.
conformation, CO conformation, CS conformation, and we look into this transmission next slides. Biocompatibility testing, if you are having good correlation with biology paper, biotechnology or any other, so you can go for biocompatibility testing of particular nanomaterial. Like they are also having collaboration with such people in our college because they are having microbiology, biotechnology. We are also going through this and optimization of reaction potential. So you are using our protein any reaction or like fiber preparation, any from preparation, but the what kind of conditions or reaction conditions required for to exhibit the chemical activities. This optimization of reaction conditions. So industrial with sugarcane I discussed that we produce a lot of industrial sugarcane waste because there are so many sugarcane industries and even in Vidarbha, is known for sugarcane production industries. I think in that way we are quite similar position. So we are generating this much amount of this is the data of 2020 that 24.900 data we are producing that sugar production in Chhattisgarh. But here we are producing in fiscal year 2023 that 56,000 kilograms of the sugar per hectare. So in this sugar case, which we are generating. So here is the solution. Hydrogen and green synthesis, organic synthesis, because we need solvency for pharmaceutical application, we need to prepare core molecule as a drug design, or design for microscopic molecule, we need to prepare for various medicinal application. But for that, we are using such kind of catalysts like PD, AU, AZ, metal-based entities. So first and foremost, they are expensive. Secondly, they are vanadium or vanadium oxide catalysts are toxic in nature if you are using them as a catalyst. So here we are trying to find out some non-toxic biodegradable material and which is generated waste sustainable and which gives a very good catalytic activity which is having. So the nanomaterials can be a very good alternative because they have high sophisticated chemical electronic structure and easy to functionalize. So here, I'm discussing today the carbon content. So these are the types of carbon dots as we seen in our last lectures. 10 to 100 nanometer range should be there in at least one dimension of the molecule. All the three dimensions of the molecules are having less than 10 nanometer, then it is considered as a carbon dot. If you are preparing this the body the use of carbon, then it is carbon dot. And quantum terms is coming from that quantum effect. Quantum effect is showing that quantum effect. That's what the terms came from. And because it is generated from carbon, it is generated from iron. So this is low toxic, biocompatible, and high catalytic potential. So I think though people don't confuse with in research. It is called quantum dot and carbon quantum dots. Quantum dot is not a if quantum dot is not biodegradable, but when we talk about carbon quantum dot, it will come under biodegradable and biocompatible category. So, what is our resources? We have waste resources such as sugarcane bagasse. When when you extract the juice from the sugarcane and the material left, which is known as sugarcane bagasse. So we are preparing this which I have discussed. Why sugarcane bagasse? We will prepare because it will be cost effective and the particle size we got from 0.75 to 5 millimeter particle. Exhibit strong resistance property, high water solubility, excellent biocompatibility, and they are showing good anti-bacterial, anti-infectious, antimicrobial activity. So this is the core idea. Convert sugarcane waste into valuable carbon quantum dots. So we are basically creating this to wait. And again, the organic synthesis part, we are trying to use a green chemistry because we are replacing the hydroxide metal oxide nanomaterial catalyst uh, carbon from the top. So this is a green approach for organic synthesis and that utilizing local resource. So this is a green cost effective. So this is sugarcane bananas picture. As you all have seen this. So these are the methodology, installation, processing, and so many processes are there for the generation of carbon dots, top-down approach, bottom-up approach, and chemical method. So many methods are there. But here we need using hydrothermal method or microsynthesis method. So microsynthesis method we are yet to work the only one from this hydrothermal methods. We already process our paper and after preparation you have to go with the analysis, look the visible NPR, deciding them, and no doubt if you want to go for further application after graduating studies, hydrothermal processing. So now it will be what as I discussed earlier, we use studies from native grass, rice grass, sunflower grass. These are the local grass available in Chhattisgarh or even across the India. So we already published the paper in that cycle, derived silica nanoparticle and carbon nanoparticle and its application in organic transformation reactions already published in the paper. And right now we shifted to this sugarcane bananas and we got projects, we got CG corporate from Chhattisgarh Council of Science and Technology this work and we have extended that work to more. So we are using that hydrothermal process. So what is the hydrothermal process? So we take the gas, we do carbonization in our. I'm doing this experiment in my college. So I am like college teacher. So we are in the lack of infrastructure and lack of facilities, loaded with lots of classes, but it's still want to decide then what we do. So we have to prepare nanoparticle in our lab. I think it's very simple chemical reaction method, hydrosimple method, and microsynthesis is very, I think, very important for this method. And people also mentioned. So I am trying to listen for analysis for net prediction. Definitely, I'm going to IIT and this calculation you go for I will discuss this in details. Nanosynthesis. This is auto clear. So I try to purchase this and I got this just 2.5 or 3 lakh all these materials and there was a small lab. Although we have 3 labs, but I want to work on materials. So catalyst, so we got the carbon dot we use catalyst and after that we test it as a organic catalyst reaction. So this is the funny question and CW what? Simple sugarcane bagasse. When you eat it, first of all, you have to take the sugarcane bagasse, wash it properly with the orange water, and heat it for 2 to 3 days in sunlight. And after it dried, you have to put it in a hot air oven for 60 degrees for 3 hours. 70, 60 to 70 degrees, and you will get this carbon. And after that, you have to distribute it and mix with ammonia till you get the 7 pH. Then you have to put this mixture of compost powder plus citric acid plus ammonia in an autoclave in 200 degrees for 6 hours, and then we get this powder. If it's liquid, you will get black in color. Again, you have to go for after this. You have to go for solidation for 1 hour, and after beating after 1 hour, you will get some dissolved particle and you will get some undissolved. So that undissolved particle will you have to remove by using 600 RPM for 1 hour or 60 minutes. You get the supernated solution that is carbon monoxide, but how you will we go for that dilution. And we will go for dilution. For dilution, we will get this kind of color.
But after getting little dilution, you will see that you will put this vessel in a UV chamber, you will get this color. Pattern fluorescent color. So as you know that that means color. So I am not done with. So this is the time limit and this is for 10 minutes. This is 5 nanometer. That means the carbon we got 0.7 3.5 nanometer. And this is what the say, and this is particle size analyzer. We go for DSC study and we draw the graph and we you see that the particle size is magnified from 0.5 to 3.5. But every particle size you can observe is 105 to 2.0. That means it comes under 10, that is it, 10 nanometer category. So here we are going in the right direction. And this is the exact diagram and then I took the angle from 10 degree to 80 degree and you see the light from 21 to 28. This is silver or this is basically from 0 to 9. So this is the acceleration that carbon this is the proof that we have a carbon in our compound and the size is less than 5 nanometer. So we got the carbon dot, but the average it is random distributed and average particle size is 1.5 to approximately. And this is LPR spectrum, so by meaning LPR spectrum. LTR spectrum, we know that it will help to explain the spectra, UV visible spectra, that what kind of stretching or bending is going on or anything stretching or any particular condition. And if you want to go for antibacterial or any other anti-inflammatory activity, then you need a lot of polyphenolic, you need to have a lot of polyphenolic group in your compound. Whatever biomass you are using, you may be taking leaves, neem leaves or any kind of leaves. So these leaves are heavy or very nanometers or heavy lots of polyphenolic compound and this polyphenolic compound is a reducing agent. And this will help you to produce carbon monoxide. As well as they will help you the fluorescent activity that C double bond C and C double bond into phytoplankton and into phytoplankton conjugation will give a fluorescence conjugation of these two. And as well as that the polyphenolic B has very good anti-bacterial so it will help to enhance the anti-bacterial activity of carbon bottom of what we are getting from biomass. So again, this is UV and this is definitely we are giving this 2 weeks. This is very much 33 and this is 330 2 mm. So this is coming comes from pi to initial C double bond C and this is coming from C double bond and into transition and as we see that this is that due to that phytoplankton transition conjugation and we took the range from 200 to 600. So these are the few reactions we proposed that we are working oxidation and reduction and oxidation. But we part of this reaction, the nutrition of benzoyl into oxidon and benzene the inverted synthesis. And the reaction is going on very well, continuous nowadays. And we have been taking that 2-aminophenol and every high. We use the hormonal series of and high formula various kind of substitutes like nitrochlorothiazide and we are getting then compound. So this is the basically and this type of product we have prepared and we got this much in 98%, 94, 93, 96 and the one and we use the use of it this is the noticeable ethanol and water and the reaction is If you mix it to the microwave, the reaction will be much more faster. But we could not go for that yet. But we are planning. So this is again the bento also strong derivative. We have used this just stage. So to aminophenol and aldehyde and we got the bento also strong. So we have prepared this six derivatives and here you can see that the eight of these compounds are 92% to 98%. And the reaction temperature is at room temperature and the reaction temperature also using ethanol and water. No previous solvent, no water solvent. We are trying to move our reaction towards three direction. So again, these are the benching same, and these are the possible mechanisms because carbon dioxide are having high surface area, so they are providing to interact with the two different molecules, and thus they are see the rate of the reaction. So reaction time is decreasing, and the reaction is occurring at room temperature. So the conclusion is that the isolation of the product is very easy, and sugarcane occurs that carbon monoxide might be a promising ingredient as a catalyst for the heterocyclic organic compound transformations. And again, this reaction took this 10 to 15 minutes. Within 10 to 15 minutes, we have prepared this, and the separation was not tedious. We did not use color chromatography. Just we just digestion process with the ethanol and the water product. So this reaction is very easy to just within 10 to 15 minutes. It's hot and very good. Just figure and efficiency. So these are the reaction optimization. So we try various kind of solvent, lithium, MEC and BMF. But as you see that ethanol and water are the most relevant solvent for this. And among the ethanol and water, 1:2 ratio is the matter. And the amount of the catalyst 10 milligram is vanilla. This is the condition, but this is the optimized situation of the reaction. And again, same is the mechanism. And we try to check the reusability of catalyst, whether the catalyst is reusable or not. It was reused up to 10 times, only 17% that catalytic activity of C2 has increased. So it is quite significant. So the transistor phosphates, so carbon promising candidate for the heterocyclic or for molecule synthesis. These are the sustainable solution and so it can be promising an alternative for a better alternative for the metal oxide nanoparticle or heterocyclic that is metal oxide techniques which have been using these days for organic synthesis. So recyclability, biocompatibility, that's this we are going to these days and we got very good result. We tried with 6 bacteria in complexity and contaminated. So we got a good candidate in this. But this process, I did not show here. And these are the outcomes. We got a biocompatible carbon dots with high efficiency and catalytic performance data. And they are very useful for the organic transformation rate. And they are less expensive, unlike the metal oxide and hydroxide, non-biodegradable catalysts. So it can be better than so is that support agro industry, waste management solution, promote green technology, boost regional research, and improve waste startup. So we have recent colleges that we are having MOU with startup, agro-waste, and we are working with them on this work. But we are preparing nanomaterial which is suitable for market, so they are doing that. This is the insights, digital circular economy, scientific transfer, social benefit, increase for in hundreds. So thank you very much. Enable summary the applications State University of Gujarat University. They are completing my PhD, and of course, I'm getting support from CSNCRI, Management Institute, for categorization, and my own college, and this is going to have one of the faculty, was my co-guide during my PhD. He is also my mentor, and this is my college team. These two people are from Cyprus, both are sugarcane business started. These people are also working with us. And he's a researcher. He's one of my research scholars who are using it for the last time.
In the review session, the Dr. Rachel explained the definition as well, because the is not the definition, but he has taken a lot of papers and he has, the expert research and discussing about the last week also what are research is important for research. He discussed about the objective carbon control box from certificate based and it's a different director visualization will be into the sustainability. Therefore, in Chhattisgarh, yes, the good one, and Maharashtra, this presentation is for only research is for without researcher we cannot get the exact result. Because this now most of the industries that on the PhD without the one science and basis. But she has given the example. So what are the research? What is the research activities and what is the policy of research? Therefore, all the researchers sitting here, you have to take initiative, you have to take guidance, and you have to motivate, and you have to of research. And you have the research point in India. Okay.
Yes, indeed, sir. Actually, this technical session had a wonderful exchange of knowledge, both offline and online. Now, on behalf of organizing the meeting, I request for the future persons to please present a certificate, sampling, and details to the resource person, Dr. Azra. Welcome. Anyone request to please let me know in advance certificate to respected chairperson, respected fathers. Yes. We also have the police practices and now this Kerala and mental and certificate. It's a very teacher in full talks the field of advancement review. Also extend my sincere thanks to all the presenters, participants for their valuable contribution.
We consider it. Request of participants to read the chart. Thank you. The content can be complaint.